Alright, good day guys. How are you all doing? In my previous class, I talked about the oscillation, and I told you guys that under wave and acoustics, the first thing we have is oscillation, and inside oscillation, you have the simple harmonic motion and the rest. So bet me, I would love to break this thing step by step so that it won't waste much more time and you won't be spending a lot of time on one thing. So under simple harmonic motion, we have this to explain, but these characteristics of simple harmonic motion, I will try to create a video on it, different videos, so that you can understand every bit of it, and mainly this is what it tends to be and some other addition things. So I'll be explaining the characteristics of simple harmonic motion and the equations of simple harmonic motion, yeah, in next slide. But for today we are just to explain simple harmonic motion in whole. Now you see, when you plug a guitar string, you can see that the sound has a steady tune and lasts a long time. Yes, most cases when you plug a guitar string, if you are someone that have used guitar before, and if you plug this guitar string, you know it moves faster, more like it vibrates, but for a single pendulum it oscillates. Now let's move on guys. It says that the strings of the guitar vibrate around the rest equilibrium position. Now if you are to look at this guys, let's say this is the one of the guitar string. When I plug the string of guitar, it moves here faster, come back here, so like that until it gets to this equilibrium rest position back. This is called the rest position of it, and as you can know, it moves to, we can say, call this a positive a negative a. It moves like that, vibrating through the equilibrium, come to the equilibrium, go back again, come to the equilibrium, go back again, like that until it comes back to rest, and it is faster. Then let's move on guys. That is one thing I want you guys to understand. You see, one oscillation is completed when that strings move like that about its equilibrium position back. What do I mean? One oscillation is completed when the string travels to what? To an extreme position here, and what? And other extreme position here, as you can see. Then, like I said, one oscillation has been completed. So when I plug the string of guitar and it goes like this and comes back like this, one oscillation has been completed. And you all know that since it moves, it comes back to its normal initial position. That is one thing I want you guys to know. Then how does this happens to affect what we call this periodic motion? Now you see, the periodic motion now is a part of any motion that now repeats itself at a regular time interval. Now if you look at this now guys, looking at the guitar string, it doesn't just go like this and come back then rest. No, it moves like this, it goes to the extreme end, come back again to the other extreme end, like that, periodically. Are you getting what I'm saying? So in a nutshell, we can call this string of guitar a periodic motion. Now if you are to look at this guys, moving to some important things, you see this, that is one aspect of a periodic then let me explain what do we call restoring and deforming force. These two things will help you understand the equation and characteristics of simple harmonic motion I want to explain later. Now let's assume you have, so let's say you have a particular string like this. Let's say you have a string, sorry, I'm not that good with things like that. Let's say you have a particular mass here on the string M, you know, and a hook is attached to it to drag it. Let's say this is the position, the normal displacement X, right? Now if the string, this is the string on its own. Let me quickly put this is the string guys. Now you see, if a force is applied to this string, you should know that the force being applied, if you are to drag it, it will change the position to another. Let's say you are to drag it from here now, then it will change the position. Let's say from here, it might change the position to somewhere here by dragging it. Are you getting what I'm saying? Now when you drag it, the force you use in dragging it to this particular extent is called the deforming force. The deforming force. So when you drag any string, dragging it to change its rest position, that force you apply is what we call the deforming force, which is also known as mainly a net force. Now guys, most cases when a particular elastic material has not gotten to the elastic limit. What is the elastic limit? The limit whereby when there are some places whereby you will drag a particular elastic material to a limit whereby it won't be able to come back to its original position. Now we are not dealing with that. We are talking about a normal reforming and a normal deforming and restoring force. Now you see guys, if a force is applied to deform the material, that means to stretch it, let me just put it that way, then what return it back to the original position? What return it back to the original position is what we call the spring force or the restoring force. Are you getting what I'm saying? The spring force or the restoring force. And if you guys are to look at something, you see that they are actually acting in both two different ways. That is the force applied to move it like this, and the force applied to bring it back to here. You can see that they are more like acting in inverse to each other. That was why if you are to look at Hooke's law says that the force is direct proportional to the distance. Are you with me? Now the force this is talking about is the deforming force that Hooke's law was talking about. And most cases now, if you guys are to look, you can see that the deforming force, the restoring force, you can even say the restoring force is equals to the negativity of the deforming the deforming force is equals to the negativity of the restoring force. And what do I mean is that if F varies directly, that's the force being applied to deform the particular material, varies directly as the what? As the distance of the particular material. Then you should know that under Hooke's law you have your F equals to Kx, right? Yes, this is for the deforming force. Then since we all know that the deforming force is equal to the negative of restoring force, then what is needed in simple harmonic motion more is that we can easily say that the force is equals to negative Kx. That is how they are being gotten. So the F equals to Ks and F equals to negative Ks is due to the restoring force and the deforming force. Why I'm explaining everything now is simply because you will need all these things when we start explaining the characteristics of simple harmonic motion and the equation of simple harmonic motion. Now moving on to this now guys, then how can we define the reforming force to make it much more understandable? It says restoring force is the force that brings the elastic material to its equilibrium position, to its rest point. That is, brings it back to the rest point. While the forming force, are you with me, is that particular force that is applied to what? To drag a particular elastic material from its equilibrium position. Then moving on to this now guys, we have the sinusoid, which is also called the we also can only call it sinusoidal wave also. Now you see the sinusoid, what I actually want to explain the sinusoid is on a different wave on its own. It's on a different wave, on a different level on its own. Yes, simply because I'll be explaining sine wave and how sine wave helps in discovering some equation of simple harmonic motion. Most people they find it confusing when they saw cos th. How does this cos come into play? How does this sine comes into play? Yeah, I will explain that. And what does a sinusoid means? Why I'm trying to explain all this is just to give us a good and better definition of simple harmonic motion. Now guys, let's move on. It says that what? A sinusoid is like a periodic wave, and since I've explained what they call periodic wave, moving like this, moving more like that, going back like that, like this, like that. So it's more like a periodic wave whose shape, that's the waveform, is in trigonometric sine function. So if you are a student who do not understand mathematics, I will drop wave representation. That's graph of trigonometry also, and sines of trigonometry, because of everything mainly categorically that will help you in simple harmonic motion. I will drop that so that you can understand how all these things are being gotten and what is the amplitude, what is this, what is that. Now guys, I said I want to talk about the period and frequency. In our next slide I'll talk about the characteristics of simple harmonic motion. So I'd explain all these things to help us understand this first thing better. Then moving on guys, now let's now define periodic motion on its own. You see, a periodic motion experiences, you get what I'm saying, that kind of motion a particular object experience by means of restoring force. Are you getting what I'm saying? Restoring force whose mass is directly proportional to the distance, as you can see what I was explaining the other time, to the distance of the object from an equilibrium position. Then it acts toward the equilibrium position, just like what I had explained already. So that is what we call periodic motion, nothing more, nothing less. Now talking about the period itself and frequency in oscillation. Period and frequency in oscillation. Before we talk about the simple harmonic motion at large, then we cover it up for today. Now you see, this results in an oscillation that is described by a sinusoid. That's both the period and frequency. They result in a particular oscillation that is only described by this sine wave. That's why I said sine wave is very, very important, and we will explain that. Then it says that it continues indefinitely, and if there is no friction or any other dissipating of energy, that means if it is in a free space, it continues like that indefinitely if there is nothing to slow it down or any damping to try to control anything there. Are you getting what I'm saying? So since we know that friction is absence, are you getting what I'm saying, then the time to complete one oscillation is going to be constant. That is, nothing is slowing down, so it moves on like that regularly. It's in a constant interval. Then it is constant, then it is called the period. So therefore, since we know that the friction is absent there, then the time to complete that one oscillation, are you getting what I'm saying, is constant, and that is what we call the period. And as you all know, our period is represented with T, your T. Then talking about frequency, you all are not new to that already. You know that the frequency is the number of what? Of, let me break down for you guys so that you will understand very, very well. It is more like the numbers of, let me give you guys one or two formulas for it. You see, most cases they do say F is equals to N over T, which I will come back to that. Then frequency itself is the number it takes for that particular period to that particular oscillation per the given time. But how does this effectively, or how does this come into play? Now look at this now. When you deal with periodic motion, you can't define frequency in that manner. You have frequency dealing with normal wave, frequency dealing with different thing. But you need to understand one aspect of frequency, which is the one we are talking about, which is the period. Now you see, for period, frequency is the number of oscillation. Are you get what I'm saying? Then per the unit time. And since it is the number of oscillation per the unit time, that means that our F, like I said, is equals to N over T. And I told you guys that in most cases it deals with a constant thing where there is absence of friction, and it completes one oscillation when it does a turnover. And since we have that, we can easily say that one oscillation giving us one circle, our force can be equals to, you know, one circle per your seconds. Are you getting what I'm saying? So your one oscillation per the given time, and your frequency is measured in hertz or per seconds. Per seconds or hertz. Per seconds or hertz. So like I said, in our next class I'm talking about the characteristics of simple harmonic motion. But let me bring this into your ear, guys. There are the frequency human being can actually attain in listening to sound is 20 to that's 20 hertz, so that should be to 20,000 hertz. If that is not correct, you can, you know, try to put that. So 20 to 20,000 hertz, that is for the total frequency human being can hear. And most cases you guys will see that some dogs, you get what I'm saying, do bark sometimes. Why is that? They call some things ultrasound. That's ultrasonic sound. Dogs has much more higher frequency, which tells them a little bit probably that they could listen to some ultrasonic sounds, which human being can't. Are you getting what I'm saying? So mainly frequency is much more higher. Are you getting what I'm saying? In terms of ultrasonic sound. But for human being now, it is lower, a little bit lower. That's for the animal, a little bit higher, like dog. For human being, it is still lower compared to that of the dog horn. So like I said, mainly we need to understand some theoretical aspects of this, which I'll just break down. In our next class, I'll talk about the characteristics of simple harmonic motion and the rest. So for now, you just need to understand these things before you start bumping into formulas, before you start using formulas to solve some questions, so that you can get what? The deep knowledge of what you are dealing with. Thank you so much.